For decades, the Linux kernel has been built on a single unshakable foundation, the C programming language. C has been there since the very beginning, powering everything from tiny embedded devices to the world's largest supercomputers. It is fast, flexible, close to the hardware, and brutally unforgiving. That last part has always been both its strength and its weakness. The Linux kernel's history is filled with legendary engineering feats, but also with countless security bugs, memory corruption issues, buffer overflows, use-after-free vulnerabilities, and subtle race conditions that only reveal themselves under extreme pressure. For years, developers have tried to mitigate these problems with better tooling, static analyzers, code reviews, and sheer discipline. And now, something remarkable has happened. Linux has just made Rust permanent, and that decision quietly marks one of the most important shifts in the project's entire history. When people first heard about Rust entering the Linux kernel, many assumed it would be an experiment, a temporary side project, or a niche curiosity that would fade away after a few releases. Linux has always been conservative at its core. It evolves constantly, but it rarely abandons its foundational principles. The idea of bringing in a second systems programming language sounded radical, even risky. Yet today, Rust is no longer a trial run or a controversial experiment. It is officially part of the kernel, with long-term support, a growing set of infrastructure, and a clear future roadmap. This is not Linux trying Rust anymore. This is Linux committing to Rust. To understand why this matters so much, you have to understand the scale and nature of the Linux kernel itself. The kernel is not an application, it is not a library. It is a living organism made up of millions of lines of code written by thousands of developers over decades. Every line of kernel code runs with the highest possible privileges. A single mistake can crash a system, corrupt data, or open the door to attackers. In user space, a bug might crash a program. In the kernel, a bug can bring down an entire operating system. That is why kernel development has always been so careful, so slow to adopt radical changes, and so resistant to trends. Rust enters this world with a very specific promise: memory safety without a garbage collector, combined with performance comparable to C and C++. Rust's ownership model, borrowing rules, and strict compile time checks are designed to eliminate entire classes of bugs before the code ever runs. Use-after-free errors, double freeze, null pointer dereferences, and data races become either impossible or extremely difficult to express in safe Rust. This is not a theoretical benefit. These exact classes of bugs have been responsible for a huge percentage of critical Linux kernel vulnerabilities over the years. The decision to make Rust permanent in Linux is not about replacing C. That is a crucial point that often gets misunderstood. Linux is not being rewritten in Rust, and C is not going anywhere. The existing kernel codebase is massive, stable, and battle-tested. Rewriting it would be impractical, risky, and unnecessary. Instead, Rust is being positioned as a complementary language, especially suited for new code, new drivers, and new subsystems where safety and correctness matter the most. Device drivers are a perfect example. Drivers account for a large portion of kernel code and an even larger portion of kernel bugs. Many drivers are written by hardware vendors who may not be kernel experts, working under tight deadlines, and maintaining code across many kernel versions. Memory safety mistakes in drivers are common, and they are a frequent source of security vulnerabilities. By allowing drivers to be written in Rust, Linux provides a safer default for new driver development without breaking compatibility with existing C drivers. What makes this shift truly permanent is not just that Rust code can exist in the kernel, but that the kernel now includes stable Rust abstractions, build system support, and a commitment from maintainers to keep Rust working across releases. Early Rust for Linux patches were fragile and experimental. They relied on nightly Rust features, lacked proper abstractions, and required constant rework. Today the situation is different. The kernel has a defined Rust toolchain version, clear guidelines for Rust code, and a growing ecosystem of kernel-level Rust APIs that are reviewed and maintained just like their C counterparts. This permanence also reflects a generational shift in kernel development. Many new developers entering systems programming today are learning Rust first, not C. Universities, online courses, and open-source projects increasingly emphasize Rust as a modern systems language. By embracing Rust, Linux is making itself accessible to a new wave of contributors who might otherwise be intimidated by the kernel's complexity and the dangers of C. This is not just about safety, it is about sustainability. The Linux kernel needs new developers to thrive for the next 30 years, and Rust is one of the tools that can help make that happen. Of course, this decision was not made without controversy. Linus Torvalds himself has a long history of skepticism toward complex abstractions and language features that obscure what the hardware is doing. His support for Rust did not come easily, and it came with strict conditions. Rust code in the kernel must not make things worse for C developers. It must not introduce unnecessary complexity. It must not force kernel maintainers to become Rust experts overnight. The Rust for Linux effort succeeded precisely because it respected these constraints, integrating Rust in a way that coexists cleanly with C rather than competing with it. One of the most interesting aspects of Rust's permanence in Linux is the careful boundary between safe Rust and unsafe Rust. The kernel cannot be written entirely in safe Rust because it fundamentally interacts with hardware, raw pointers, and low-level memory operations. However, Rust allows these dangerous operations to be isolated in small, well-reviewed, unsafe blocks, while the majority of the code remains safe. This dramatically reduces the surface area where bugs can occur. In C, everything is effectively unsafe all the time. In Rust, unsafety becomes explicit and contained. From a security perspective, this is enormous. Many security researchers have pointed out that a majority of serious kernel vulnerabilities are memory safety issues. If new kernel code is written in Rust, those vulnerabilities simply never come into existence. That does not mean Linux becomes perfectly secure overnight, but it does mean that the baseline improves steadily over time. Each new Rust driver or subsystem is a small step toward a safer kernel. The permanence of Rust also sends a powerful signal to the wider open-source ecosystem. Linux is not just another project. It is the foundation of Android, servers, cloud infrastructure, embedded systems, networking equipment, and countless other technologies. When Linux commits to a language, that decision echoes everywhere. Toolchains improve, libraries mature. Companies invest, developers take notice. Rust's inclusion in Linux validates it as a first-class systems language in the most demanding environment imaginable. There is also a cultural dimension to this shift. The Linux kernel community is famously opinionated, sometimes abrasive, and deeply rooted in tradition. The fact that Rust has earned a permanent place there means it has passed one of the toughest tests in open source. It had to prove not just technical merit, but also long-term maintainability, clarity, and respect for existing workflows. This was not a marketing decision or a trend-chasing move. It was a hard-earned acceptance. Looking forward, the real impact of Rust in Linux will unfold slowly. You will not wake up tomorrow to a kernel that is suddenly different. Instead, over the coming years, more drivers will be written in Rust. More abstractions will stabilize. More tooling will improve. The percentage of kernel code written in Rust will grow gradually, almost invisibly. But the cumulative effect will be profound. Fewer crashes. Fewer security advisories. Easier onboarding for new developers. A kernel that remains fast and powerful, but becomes safer and more resilient with time. It is also worth noting what this decision does not do. It does not invalidate C knowledge. It does not devalue decades of kernel expertise. C developers remain at the heart of Linux development, and they will be for the foreseeable future. Rust is not a replacement, but an addition, a new tool in the toolbox. The permanence of Rust is about choice, not coercion. In many ways, this moment represents Linux growing up without growing old. It shows that even the most established and successful open-source project in history can still adapt, learn, and evolve. Linux has always been pragmatic. It adopts what works and rejects what does not. Rust's permanence is a testament to the fact that it works, not just in theory, but in the harsh, uncompromising reality of kernel development. So when we say Linux just made Rust permanent, we are not talking about a single merge or a single announcement. We are talking about a philosophical shift, a long-term commitment, and a quiet revolution in how the most important software in the world is built. It is the story of a project that values stability enough to embrace change, that respects its past while preparing for its future, and that recognizes that safety and performance do not have to be enemies. Years from now, when people look back at this moment, they may see it as the point where Linux took a decisive step toward a safer and more sustainable future. Not by abandoning its roots, but by strengthening them with a new language designed for the challenges of modern computing. Rust is no longer a guest in the Linux kernel. It has moved in, unpacked its bags, and become part of the family. And that changes everything, even if most users never notice it happening.